Hello, welcome back to Stat 3050 at the University of Wyoming. We are still online, but we are still having a good time. Okay, so today I've got an example in multiple regression, how to do it in R per usual, and sort of picking the best quote-unquote variables and the best quote-unquote model, all of that. And then we're also going to be doing a bit more with some different packages, which is awesome. Some new libraries that we're going to be working with. So today we're going to be looking at how to find correlations between all the variables. There's a really good package, that psych package, makes a nice correlation matrix and plot matrix for us, which makes things so easy. And then actually building a multiple regression model, and then trying to figure out which variables are necessary and which ones aren't, and then maybe picking a good model itself too. And then, so I've just mentioned that psych package, and then the CAR and the LEAPS packages, those help us do model selection, making model selection a bit easier, which is great. And then number 4, sort of using R-squared adjusted and this BIC, this Bayesian information criteria, to figure out which model is the best. So with all of that being said, we are sort of getting into the world of subjectiveness in statistics, and so it's not necessary to make every single model, right? I certainly won't be. I will be making, in these examples, maybe like 2 models, maybe 3, kind of depending on what's going on. But when you're off and doing this on your own in homeworks or labs or in your own work, you might make a model, a multiple regression model that is totally different than your lab mates or your classmates or something. And there's pros and there's cons of every model. But the nice thing about stats, for the most part, is that you can make a model, and if you have enough reasoning to back up your model, then you're not wrong. Stay away from saying that everyone is right. But not everyone is wrong when we're looking at model building. So just sort of keeping that in mind, that also means that I'm only going to be making maybe like 2 models in every example, because there's just so many different combinations of variables and so many different models, so many different reasonings that make it all, kind of complex as far as, what is good and what isn't. And so these videos also should only be like 20 to 30 minutes long. And if we were to go in and make every single model, these videos would be like, I think 7 hours long. So we're not going to worry about doing every single combination. I'm just going to be doing what makes sense to me, and then sort of going from there. Okay, and then per usual, this example is brought to you by the comment. This is new. They kind of sound like they're from the 70s. So these, I listen to music pretty much every time I make these videos, and these 2 albums, super good. That's what I've been listening to a lot. Joey Dosick and then The Dip, 2 very soulful bands there. So, all right. Anyway, enough about music, enough about the subjectiveness of statistics. Let's go into R. Okay, so here we are. The first thing I want to do is I want to set my working directory to my multiple regression folder, which I've got here. So I'm just going to hit that. And then I'm going to copy and paste this so I don't have to do that every single time. Every time I run the script, now it will do it automatically. So that's good. And then I want to read in the data. And the data that we're working with today, it's very interesting. It's human weight data. That example, I use it all the time, height and weight, all the time, trying to relate 2 things together, especially in the context of simple linear regression. Height and weight do a pretty good job of explaining each other. However, this data set that we have has a bit more to it. So let's actually take a look. I've got it called weight. I'm going to call it weight in R, but in the CSV file, it's just called weight.csv. Okay, so I read that in. Let's take a look. We have 241 observations of 10 variables. It's kind of a lot. So what's the goal? Well, maybe let's take a step back and just look at the data. What's our outcome? Well, the outcome is weight here. We're trying to model weight based on all of these other measurements we have. So we've got height, neck circumference. I believe everything after this I believe they're all circumference measures for the most part. But it doesn't really matter so much what the units are, but they all are here. So that's good. And we want to take all of these and see which ones are good, or what combination of variables are good at explaining weight, sort of modeling weight here. Maybe the purpose of this study or our analysis is just finding a relation between all of these variables and weight. Maybe we want to predict weight based on the data that we have, these 9 variables here, these 9 predictors. Who knows? We'll treat it as both for right now, because we have enough experience to where we don't have to kind of get hung up on all of the p-values and estimates and everything like that. So let's go ahead and do this. What do I want to do first? Well, it's kind of good practice to get into doing a summary of the data and then checking the structure of the data. So I've just ran both of these, but let's take it one line at a time here. So the first thing, looking at the summary, this just gets us sort of what we call anthropometric measures, summary measures here. You might want to report these. Most likely, you'll just report the mean of each of the variables here, not so much this 6-number summary. So when you're writing and papers and doing research presentations, these are good values to report, but for this class and this analysis, not too important. But always good practice to kind of get into that. So let me do this real quick. Summary, spelled right there. Okay, and then the structure here. This is important in our analysis. We just want to make sure that all of these variables here, we know they're all numeric, they're all numbers. We want to make sure they're being stored as such. Sometimes when there's missing data, the good practice is to just do an NA, leave it blank, right? The computer looks at the blank cell and will put in an NA value there. So it's easier to work with for R, at least. However, sometimes people put in like a dash or a period or something, even the word missing. And if the computer, when the computer reads that, it's not going to read that whole column anymore as numbers. Since there's a 1-character cell in there, it's going to read the whole column as a character. So just checking the structure here is good practice just to make sure there's nothing like that going on. All right. Okay. So what do we want to do next? Well, another good thing to get in the practice of doing is another sort of double check. And I'll make this like a little section here, double check. Another good thing to get in the habit of doing is making sure that you don't have any redundant variables in your data. And what do I mean by that? Well, we're looking at weight. And in this case, and let me check so we can all see. To me, it looks like these are being measured in pounds and not kilograms. That's pretty heavy for kilograms. So they're being measured in pounds, and it's data that's been collected, right? So what you would maybe want to check for is to see, well, maybe did somebody accidentally put in weight in kilograms in addition to weight in pounds? Because we know that those two things are doing the same thing as far as the outcome. But if we were to treat, only one column as an outcome and accidentally leave in that other weight in kilograms, those two are going to be 100% correlated, right? Which is not good. So how do we check quickly the correlations between all of our predictors and the outcome? Well, we have this really cool package called Psych. And I only use one function out of it. If you don't have this already, in the console down below, just type in this install.packages, and then in the quotation marks here, just put psych. So you can copy and paste this thing Put it down here in the console and you're set. Anyway, you only have to do that once too. So I've got it read in here. There's only one function that I use out of this library, but if you are in psychology, the field of psychology, this package is used all the time in their own sort of way. The only one function that I use out of here is called pairs.panels. You don't need to save it as anything. We're just going to run it by itself. And let me give myself some more room here too. Okay. And what does this do? Well, if you're very curious, and we can do it ourselves too. If we do a question mark down here and then pairs.panels, run that, it'll bring up this nice little help window down here. And it's got everything. It's got all of the arguments in here, all of the default settings and sort of the null settings, and then all the details and whatever else. So that's cool. We can read through that on our own time. I don't want to do it now because I don't want to bore you. But what this does is it makes this really nice correlation matrix and then a plot matrix out of the correlations. So if we were to just by itself put in our data, and that's all you need to do, you don't have to subset it, you don't have to divide it up in any kind of way. If we were to run this, if we were to hit comma and then tab, or tab at the very beginning of this function, we'll see all of the options we have to kind of tweak the plot. This figure that just got made for us. All sorts of stuff, right? All sorts of stuff. So there's really only, I think, 2 things in here that we need to fix. The first one, if you look over here, if you remember, there's like this kind of red dot, red mass in the middle of the thing. That's called an ellipse. We don't need that. So we'll just, we'll do this ellipses. We'll set that to false so it doesn't do that. So when we plot that, we'll notice, if we zoom it in, that's gone now. But another thing we notice is that these lines, this red line here, if we really zoomed it in, it's not straight. It's got that lowest curve to it, which we don't want in this case because kind of traditionally these correlations are correlated around a straight line and not this lowest line here. So let's fix that too. So we just do LM equals true. That's just part of the options we have. Run that, and we'll see that things straighten out. Okay, so what do we want to do next? Well, let's just go ahead and make a model and see what's happening. I'm just going to call these models because we're going to make a few just to see what's happening. So the first thing I want to do is, at least in what I do in my own practice, is that the first model that I make, I'll call it model, and it's going to be an LM, right, a linear model of formula, and I'm just going to do all of the variables, every single one. Okay, I'm not going to do any kind of selection forward, selection backward. I'm not going to do any of that yet. I'm just going to see what's going on, right? So weight is our outcome, and then our predictors are these 9 other variables. Now, I could go in and type every single one. It would look something like this. Blah, 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 right? But I don't want to do that because that's going to take a while. So what I am going to do instead is shorthand it. I'm going to shorthand it by saying period, and that's just going to take everything that is left over after this, okay? So weight is our outcome, and then period is just going to be all the other all the other variables in the data. Okay, so that's good. Just leave that there. It looks kind of funky with a period and a comma right next to it, but that's just sort of the quick way of doing it. And then per usual, data is going to be the data set that we're working with, which is weight. So we run that, and we hit it with the summary.lm. Nothing fancy, nothing more fancy than simple linear regression. But when we run this, let's see what we get. It's a pretty big data set, pretty big output, so I have to take the whole window. All right, so what do we have? Well, we have like the normal output that we're kind of used to, with the only exception being there's just more of it because we have more variables that we're considering. So we see the same call. This is just the double check. The residuals here, the residuals, just a quick note, are calculated in the same way. They're still the observed value minus the fitted value, right? So it's the same deal there. We're just not able to see it as easily as far as the overall data, right? We're not able to make a scatter plot out of multiple regression. We can only do that with simple linear regression. But the residuals are still plotted in the same way. And I'll show you that here in just a second. And then we come down to the coefficients table, and we see pretty much more of the same. It's just there's more of it. So what do we do, or how do we sort of interpret this? Well, we interpret it in the same way. The only issue here is that the intercept here, it's not really an intercept per se anymore. It's just more or less a constant than anything else. And then also, this is the same that we saw in simple linear regression too. But this, when all the other values are 0, which biologically cannot happen, then the weight of this person is negative 312 pounds. Well, just not possible, right? Not feasible. But it's also not feasible that any of these values here are going to be 0, right? So just kind of keeping that in mind, this intercept no longer is really as meaningful as it was in simple linear regression. Okay, and we're also going to ignore it for right now in this moment, because our purpose is not prediction, right? It could be, because we do have a significant p-value for the intercept, quote unquote, but we right now really only care about relating these values, these variables, back to our outcome, back to the outcome, okay? So we could say, we haven't checked the residuals yet, but we could say that height, for every increase in height, weight increases by 2.3, holding all the others constant, right? Holding all those others constant. Same thing with the neck circumference. Weight increases by 1.11 when neck circumference increases by 1 unit. This whole thing, right? And we get significant p-values for everything here except for the wrist. So we could say that there's really no relationship between wrist measurement and weight, right? There is nothing there, nothing significant statistically to supply evidence that the wrist is some sort of predictor for weight. Okay, we just can't say it. There's another thing too. This knee variable here, this p-value is the only one. This p-value is the only one here that is not super tiny like all the other ones. Okay, it's kind of close to 0.05. It's still under our chosen alpha, 0.05. But just keep an eye on that for a second. And then we come down to the r squared. Same sort of thing here. We have a lot of predictors here, but which the adjusted r squared will account for. But we don't see a huge difference between these two values, which is good for us. But what we have not checked yet are the residuals. Okay, so how do we do that? Well, we want to read in the library ggfortify. If you don't have that installed, go ahead and do it now. Pause the video, and then I want to use this function autoplot. It's autoplot function. We've used this. We're really wearing out this function here. But per usual, we put object and then our model in. Our model in. And then we're going to clean it up just a little bit. We'll do this, and then we'll do this. Cool. And we run that, and let's see what's happening. I'll zoom it in here, too, so we can see. What? Wait. Here's what I did. I'm going to keep this mistake in, just so we know. And there's 2 S's in smooth here. In real life, in English, there's only 1. So let's rerun that. So we see now that, well, maybe the goodness of fit really has not been met. So we have these 3 assumptions, right? The first one being goodness of fit. So we're looking for curvature, and if there is evidence of curvature, then we have to fix that. We can't do anything with our model. And then the same thing, and then we have the equal scatter assumption, which, maybe we see here, but we don't care if we see it. Because already the goodness of fit is not been met. And then after that, the histogram, or the distribution of the residuals, should be approximately normal too. But we don't care because the first assumption was not met, right? And the order matters, okay? So we don't have that. We see there's some curvature down here. We see that all of the points, there's no points matching these points above the line. There's nothing below the line, kind of indicating curvature. And maybe it's like kind of fanning outward too. We know too that we can trust this residual plot because we have a very big sample size. If we had a smaller sample size and we saw something that looked maybe a little bit like this, maybe we could get away with saying that it's okay because of the small sample size. But in this case, we know that if we were to add more observations, it wouldn't really matter, right? Because we already have so many already. The data probably, the residuals of the model, I'll say, probably always look like this, no matter how many more data points we were to add, okay? So what do we do? So this is where we hit sort of some crossroads. And so sometimes putting it in a percentage change just kind of makes sense to do. A lot of the time, statistics has two purposes, right? The first one is, modeling or predicting something, some outcome based on some other data that we have. The other thing, though, and this is, I think it's a bigger part in statistics than the actual math, but it's the storytelling side of it all. I know that I can understand these human measurements pretty easily. My background is in physiology. However, you have people out there that aren't totally familiar with maybe some of the units of measure here. So when we say like, BMI increases by blah, 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 whatever, sure, you've heard that word a lot of the time, but a lot of people don't understand what the actual unit of measure there is. So instead of saying, for every 1 unit increase in whatever, BMI changes by something, right? Just an example. You could say, for every, percent change in one thing, BMI changes by some percent, which makes a little bit more sense as far as sort of universal understanding. So that's a big part in statistics that a lot of people aren't doing that need to be doing. Because sure, you can get fancy with the analysis and fancy with the units that you're using, but you're just going to be scaring people off. And that's not the point of science, right? We're trying to make it accessible and easy to understand so you don't have to have a PhD to understand what's going on, right? So with all of that being said, let's go ahead and make some improvements to this model. Okay. So my initial thought here is to maybe, let's just try log transforming the outcome, okay? Because I'll tell you right now that log transforming all of the predictors, there's no short way of doing it. So I'll just save us some time and just see sort of what happens there. So I'll call this model 2, and it's going to get the same stuff. It's going to get formula equals, and it's going to be log of weight, okay? Log of weight. And it's going to be a function of everything else. And just a note, too, we noticed that I think the wrist circumference didn't contribute at all in the model, right? The p-value was very high. So when we change the outcome, though, and rescale it on a log scale, maybe the p-value will change for the better or for the worse, who knows? But we'll leave it in there because, well, our first model wasn't that good, right? So we're not going to change anything other than the scaling of the outcome here. And then after that, we'll just get data equals weight. I've been at it for a while today. Okay, and then hit it with the summary.lm, model 2, and run that. And what happens? Okay, here we go, same old, just, more stuff. One thing we notice is the scale has changed. All of these values are slightly different now. That's because we have an outcome in the log scale now. So that's why these estimates are looking a little different than they were before. And we see that we still get the same p-value, or we get similar p-values, very significant, quote unquote. But here's what's changed. This p-value now for the knee circumference, right? What we were looking at earlier, I told you to keep an eye on that. That last p-value was, I think, 0.02 or 0.03. It's now 0.07, which is above 0.05, our alpha. So we can say, okay, now that we maybe have a better model, this doesn't contribute at all. enough at least to the outcome. And then we sort of see the same story with the wrist, okay? So before I go on and actually make proper interpretations, let's actually look at the residuals. Autoplot per usual, right? And then our model is called model 2, smooth equals NA. Oh my God, just all of this all the time. All right, here we go. So we run that, and let's zoom it in. And what do we get? Whoa, way decent residuals, right? There's no more curvature in them, so that's good. That's our first assumption, no more curvature. Second one being that there's equal scatter, which is great for us. And then looking at the QQ plot, all of these dots should be pretty close to the line, which they are. Maybe a little something going on here, but instead of looking at that, let's just look at the actual histogram of the residuals. And we do that by using this hist and then resid, and we just put our model in there. And what happens? Well, we get some good looking histograms, I'll tell you what. We might say that this is a little funky. If we change the bin size, it would look better, I think. But right now, this is pretty decent. There's some clumping sort of going on over here off in the left sort of tail. But otherwise, everything here looks pretty decent. It looks pretty decent. Okay, so what are we saying? Well, let's go back to the model. This model output here. Yep. And we're not going to do the actual mathematical interpretation, but we'll put it in general terms. Okay. So we have not transformed any of our predictors. We've kept them the same. Okay. They're only in this incremental untransformed state. Okay. But our outcome weight is transformed. It's log transformed. So what we're saying here is for every unit increase in one of the predictors, the outcome changes by some percent. Changes by some percent. Relative, right? It's becoming more, the picture is becoming more relative. It's becoming a little bit easier to understand. So we could say that, bringing it back to this abdomen, right? This sort of waist measurement, more or less. Sort of. Sort of. So we're saying now that for maybe every inch increase in the waist results in some percentage change in the weight, right? Some percentage change in the weight, which I honestly, that makes sense to me. Even if I didn't have the background that I do, I think that still, makes decent sense. I think a lot of people would be able to kind of initially understand that. Same thing with all the others. As height increases, as for every 1 inch in height that you have, weight is going to change by some percentage, which makes sense, right? It's a little bit easier to intuit than maybe an incremental change. Okay, so we've got that. The model itself could use some work because we've got 2 predictors now that are not contributing to the overall outcome. Okay, that's what we can kind of say there when the p-value is greater than 0.05. So let's sort of shift frames from relation to prediction. Okay, so right now the model it's a little bulky in that we have 2 variables that aren't totally necessary. That those being the knee and the wrist, right? But we also might have variables that maybe are sort of doing the same job. Maybe we could get rid of some of them and kind of lean this thing up a little bit. I guess no pun intended. I didn't mean to make that joke talking about body weight and saying that we're going to lean up the old model here, but that's exactly what we're about to do. So again, I am losing my mind, but just hanging in there. Okay, so what do we want to do? Well, let's bring in, actually, before we bring in other packages, let's make one more model by hand. And let's just get rid of those two other predictors that we saw that are not contributing to the overall outcome. So we can still do this as a function of, and then all of the variables, use this period, and then we can use a minus sign here and just put in the actual, and I'll put a space here, put in the actual variables that we don't want anymore. And so the first one is wrist, and the other one is knee, all lowercase. Sweet. And then the data is the weight. Okay, so this right here looks really funky. But just know that this is saying the log of the weight is a function of all of the data except for the wrist and except for the knee. Okay, so we got that. So we'll run that. Whoops, and let me give myself some more room here. And then we'll just do the summary.lm, model 3. All right, and let's see what's happening. The R-squareds are going to be just about the same. The residuals probably will look just about the same. But now we see that all of the predictors are significant, statistically significant. All of the p-values are still decently low. They have changed. Because now they're pulling a little bit more of the weight, pun unintended again. But they are doing a little bit more work now with those two other predictors gone. So one more time, let's check the residuals. Let's just check them. I'm going to leave. No, I'm not. I'm going to be consistent here. And then, spacing doesn't matter in R, just FYI. So I could do this whole thing, and it probably would still work. I'm not going to do that though, because aesthetically that looks bad. And then the smooth color equals NA, and then the theme classic. Booyah! All right, we run that, zoom it in, and we see about the same picture, right? Now that those two insignificant p-values, or those two insignificant variables, predictors, are gone, maybe the picture looks a little bit better, honestly, marginally, if anything. So it's fine. Well, I'm not going to look at the histogram, not because nothing is being violated here, but because we already have an idea of what it all looks like. Just me being liberal. Okay, so now I want to know, well, how many variables can I get away with leaving out? Which ones aren't totally necessary, So if our purpose was, relation, then, we were done at the very beginning. We knew that once we log transformed it, once it looked fine, the wrist and the knee didn't really do much, and all the other ones did, so that's good. If we're now going for explanation, having all of these variables in here might be a little difficult, might be a little cumbersome to explain. Maybe you could get away with doing it, which is fine if you can, but maybe we want to kind of thin it up a little bit to make it, a little bit better. If our purpose is prediction, we could be done here. With all of these significant p-values, the residuals are good, we're set, right? But let's for now, let's say that we want to predict and also explain. Have a pretty simple model that's leaned up, so we don't have to worry about all these extra things going on in there. So how do we do that? Well, this is where it becomes not onerous, but it does become important that we pay attention, because there's a lot going on here that can get sort of mixed up. So, and I'm going to try to notate this as best as I can. So the first thing I want to do is load in the Leaps package. Okay. If you don't have that already installed, you can just, install .packages. You can do this for any of the packages that we've been working with. And then it's just Leaps. And what this is doing is it's going to make what's called a best subset of variables for us. So when I run this, and then let me give myself some more room. There we go. What I want to do is I want to save something. I'm just going to call it best subs for now. And it's going to get. And then within this Leaps library, there's a function called reg subsets. Okay, regression subsets is I think what it's short for. And it's going to get a few things. It's going to get a few things. The first thing being, if you were to hit tab, it's asking for an X for a design matrix. We could save all of our predictors into a new data frame, or we could use square bracket notation, or we could do blah, 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 blah. I'm not going to do that. What I am going to do instead is just put in our original formula, which is going to be the log of weight as a function of everything except for the wrist and the knee. Okay. Where is the specific argument here? Well, there really isn't one. This works just fine. But you do have to leave it blank. There's no extra argument that goes in here. So just FYI, you don't have to be super detail oriented here, because if you do, formula equals, it's not going to work, right? So we're just leaving that blank. There's no formula, no argument that you have to fill in there. And then we just put in the data, right? So it's pretty much similar to the normal LM function, except you can't put formula equals. You just have to leave this line here doesn't equal anything. You just put it in there, and it does all the magic for us. So we run that, and what do we do? Well, let's just see what happens when we run this by itself. We're going to get something that's not too helpful. Here's what's happening. So we see the same call for the regression formula, and then it's saying, okay, forced in, forced out. Who really cares about what this is doing? Everything here should say false. And then the big thing here, though, is by default, the selection algorithm is exhaustive, which we've talked about a little bit before. It's using this sort of fancy algorithm to figure out which variables are the best. But which variables are the best? Well, it did not really tell us. So if we got rid of this and did maybe a summary of this best subs, what does that do? Okay. So here's what we get. Same stuff, right? This forced in, forced out. And then selection algorithm exhaustive. That's the one. You can change it if you wanted to like forward or backward. It's good practice just to use exhaustive. It might take your computer a little bit of time to figure it out, but exhaustive I think is the best one. So what is this like kind of plot here telling us? I'm going to tell you right now, we're not even going to worry about it because we have a better package that can kind of clean up what we just made here. So when you make a best subs, just leave it as best subs. Don't summarize it. Don't try to plot it. I don't even know what. Oh yeah. If we were to plot best subs just by itself, you get this really weird looking thing. Not the best. So this is not that intuitive, I don't think, at least initially for me. What we do see is that it's plotting it based on the BIC, right? And we know that the more negative the number is, or the smaller the number is, the better. I just do not know what to do with this. So let's get rid of that, because there are better ways of doing it. I'll tell you what. So now we load in the car library, right? Not named after me, I wish. But actually, maybe I don't wish that. Anyway, so within this car library is what's called a subsets function. Okay, subsets. Very important that it's subsets, because there is also a subset function in base R that we don't want to use. Okay, and then this is a little bit more detail oriented, where we can say the object now is the best subs. Okay, which is what we've made up here in the leaps package. Okay, so this is good. We don't have to do anything with this, and I'll even get rid of line 80 here, so we're not confused. We got this best subs. It's already done. It's got all the information in there that we need. We're just not able to see it as readily. So then we use the subsets function from the car library, put in our best subs model that we just made, and then what we want to do, if we hit tab, we have all of these different arguments here, but what we care about is the statistic. Okay, and if we were to, let's actually take a look at the subsets function. We can see all of the options that we have. okay, for the statistic option, which is right here, okay, which is right there. So we have BIC, the Bayesian information criteria. We have Mallow's CP, just another thing. Not worried about that. And we have the R squared adjusted, so that's good. We were familiar with that. We have the R squared, not the best because we know that as you add more variables, the R squared's always going to go up. But the R squared adjusted sort of accounts for that. And then we have the RSS, the residual sum of squares. Blah, blah, blah. Who cares? So what we're going to use for the most part, because it's more intuitive, is the R squared adjusted and this BIC. Okay. BIC, each one has its own sort of rules, but we're not going to worry about these other three here. You can see if you want, but for the most part, we're not going to worry about it too much. So in quotation marks, let's do the adjusted R squared first. So we just type in ADJ R2, which I just got from over here. Okay, the options that we have. Okay, so when you run that, it's going to bring up this thing in the plots. Okay, first off, it's a little clunky because all of this is kind of stuck together. But then also it's not going to do anything because it says locator active. Okay, what is that? Well, notice that my cursor, my nice like turquoise cursor over here, it's this sort of crosshairs. Okay, so what that's saying is, okay, locator active, that means do something else to the plot. And by do something else, what the computer is really asking for is just click somewhere out of the way of these things. And when I do that, I get a nice key here, a sort of legend. So let's zoom that in and look at this. It's my nice little plot that I've sort of made on my own. And actually, I'm just now realizing I've covered up, when I do that, I cover up the x-axis there. Okay, so that looks better. Okay, so now let me, yeah. Okay, so what is this? Well, on the x-axis, we have subset size, okay? So that's saying how many variables are being included in the model. 1, there's only 1, right? 2, there's two variables based on the best subset of variables, based on the best combination is what it's saying. 3, 4, and 5, 6, and 7. So we could do more if we wanted, but we don't have to do that because we can already kind of see that it's got this sort of curved motion to it, and then it flats off, right? It's curving upward and then it flattens off. So what this is saying is that eventually the R squareds become, nearly identical, right? Regardless of how many, the R squared adjusted. The R squared adjusted value becomes nearly identical to the other models as you increase the subset size, okay? So maybe our purpose is having a simple model, okay? I would maybe go with this one right here, this H, let's see, I guess height, abdomen, thigh, and forearm. I think I'd be okay with that because the R squared is not too much different than the next one, not too much lower, I'll say. Now, before you email me and say, hey, what's a good distance between your next jump or whatever, between R squared of subset 4 and subset 5. Whatever you want. If you're okay with saying, okay, I'm okay with sacrificing, 2% of the explained variance of y when I leave out another variable, that's fine. Some people are more than that. I know people, my advisor is one of them, that would be okay with this subset 3 here. Because if we looked at the scale, and I'm going to zoom it in here actually in a little bit. If we looked at the scale here, the jump from our subset 3 to subset 4, that's only 4%. Even less. Gosh, it's 2%. And the distance between 4 and 5 is 1%, right? There are people that are okay with this subset 2 because it's easy to explain. Height and waist size. Explaining weight. That's easy, That's very easy to understand. Totally up to you. If you're trying to build one hell of a model, then by all means do the biggest variable size, the biggest subset size, because if that's your point, that's your point. And there's nothing wrong with that. So let me real quick, let me change the Y limits here so we can kind of zoom in and see these other subsets. Let's do from like 3 to 7. We'll just try to see those last 5 there. So that's just going to be a y lim, okay, equals, and then this gets a little funky. This is a base R plot. So when you're messing around with the label, or when you're messing around with the limits, it takes 2 values. So we have to use the C, and then I'm going to do from, I think, like 0.91, and then comma to 0.96, we'll say. 0.96. So when we run that, it does the same thing, and then we'll come down here, and I think I might have cut it off a little much. Yeah, I did. Let's turn this up to 0.97, and we run that. Yeah, that looks better. Okay, got that. Awesome. Cut it off a little bit down here, but not too worried about that. So subset 1 and 2 are gone because we've zoomed in super far. And then now we have 3, 4, 5, 6, and 7. And the p-value, well, not the p-value, the r squared for this one of subset size 3, this one model, is like 0.935, thereabout. And then the next one, subset 4, is 0.955, we'll say. That's not really that big of a jump, right? 2% of explained variance. I mean, come on. If you're trying to be simple, go with this one. If you're trying to be complicated, and really trying to be very, very accurate, we'll say, for prediction or for explanation or whatever, then this is the one that you would go with. This height, neck circumference, abdomen, thigh, ankle, biceps, and forearm. So just like imagine sitting in front of a poster or giving a talk and having to say that every single time, as the height increases, weight changes by some percentage of y, holding all of these other ones constant. Same thing with neck, abdomen, thigh, ankle, biceps, forearm. Good Lord. Just all over the place, right? And that's not necessarily, maybe it is understandable, intuitive for you. Sometimes it might not be. And it's okay to pick like a smaller, simpler model, which in this case, honestly, I would go with subset 3 or maybe subset 4. I see no difference between subset 4, 5, 6, and 7. They're all effectively the same thing. So if that's not your cup of tea, let's go to a parameter that has a little bit more rules to it. So we'll replace this ADJR2 with BIC. We're going to do the BIC now. So we see the same thing. It's the opposite direction. Let me put the old legend on here. So we see the same thing. It's just in the opposite direction. Because remember that the smaller the BIC, the better, not the bigger, or not closer to 0, right? Just if it's more negative, then you're set. So what is this doing? Well, it's doing the same thing that the r squared is doing, even if we had these two plots next to each other, which let me actually see. I don't use base R that often as far as plot making. What's happening? Bad. Let me do this again. I'm going to fast forward through all of this. Good Lord. All right, good enough. Okay, sorry, good Lord. We see here that it's effectively kind of coming to an agreement, right? I've put the legend here right in the middle of this BIC one, but that's fine because we can kind of see the same situation, right? We see here that, oh wait. Okay. Lord, sorry that took so long. Okay, so it took no time for you because I sped it up, but I was wrestling with that for a while. That's okay. So what is this saying? Well, BIC and r squared adjusted are coming to the same conclusion. And we see that it's still got the same trend, right? Of course, the subset size is still going to be the best based on, what our leaps package did. It's just figuring out the best subset given the subset size, right? But what we're looking for here is just saying, okay, does the r squared adjusted and the BIC have the same sort of have the same kind of pattern, which in this case it does. And like subset size 7 on the R squared, for example, is not lower than subset size 6, right? And the opposite is not true for the BIC either, right? If there were like a discrepancy like that, then that's when you sort of go at it with your fine-tooth comb and say, okay, what do I really care about? Maybe I should just go with a simpler model, you know? Good Lord. Okay, so that took me just a little bit of time to get through as far as that code, but that is really, that's not it with model selection and variable selection and stuff, because we're going to come back to this because this data set's super rich and has a lot of opportunity for many examples in model selection, variable selection, and then just many other things, log transformations. We're going to do some interactions here in a little bit. Very, very cool stuff that we're about to get into. But hopefully this all makes sense. If it doesn't, let me do a quick sort of run through real quick. Read this looking at the correlation plot between all of the variables. Important to do, but not, you know, too important to get hung up on. Then we made a model out of all the variables. And then we looked at the residuals, found out there's some curvature, not great. I then made a second model. Okay, made a second model with the outcome log transformed. So how did I know to do this? Well, I just kind of guessed. And that's what a lot of statistics is. It's just trying a bunch of different things. It can be very frustrating and it can take a long time. But know that this is a very common thing to do, log transforming Y. If it happened that this didn't work and the residuals still look bad, then we would log transform the other variables too, maybe one at a time or all of them, and see what happens. Okay. Did the residuals, that looked good. And then I made the last model, leaving out the wrist and the knee, seeing what that looked like. And that was pretty good. That was a very decent model as far as prediction goes. And then after that, we used the leaps library to use this reg subsets function to figure out the best subset of variables at every subset size. So then, if we wanted to, we could come back to this best subsets, this reg subsets situation, and say, okay, let's take a look at the tab here, because we're just sort of tooling around now. I'm not really too worried about the details in here, but we have this n best, the number of subsets of each size to record. So what that's saying is, okay, go in there and find the best combination of variables for one subset. Then do it again, do the second best for one subset, and then the third best, or however many you tell it to specify. Same thing with the second one. Pick the first two best combination of variables, and then do it again, but just for the second best combination of variables. And then if you tell it to do it 3 times, it'll do it 3 times. So let's do that. Let's say find the best 3 in each subset size. So if we run that, and then we do all of this again, I'm going to get rid of this because, boy. And then we'll just run this. We see the same thing, except now there's 3 in each column, okay? And they're getting all hung up on themselves. And we see here that, I mean, in reality, if you want the first best, then take the first best and leave it, you know? But if you wanted to see, just curious of what the second and third best are, then you can do that with that n equals best. But we see here that they're all, you know, decently around the same size. This 7th best one, it didn't even try, which is fine for us because we only really worry about the first best. Is there anything else in here that we really care about? Yeah, okay, so we could do this method. So by default, it's the exhaustive, but if we wanted to, we could do the forward, we could do the backward, et cetera, right? So that's fine. And then there's just like a bunch of other stuff in here that we could do. Really big. That's if you have a ton of predictors and a ton of data points, right? So that's fine. Nested, we're not going to worry about that. So that's really it with this reg subsets. You have so much liberty with it as far as the best model to select, but then also the best combination of variables to select too if you wanted. Totally up to you. So with that, we are done with this time. So much. Because there being so much, I'm going to do another example just so you have it, right? This video was kind of long. I'm very sorry for that. But This is a very important subject to understand and to get a lot of practice with. So we'll move on to another example here in a little bit, and I will see you next time.